variables. So let's start with a small recap of what Pearson's correlation is. So Pearson's correlation, which we normally write as rho between x and y, is equal to the covariance between x and y divided by the standard deviation of x times the standard deviation of y. And the reason why we divide by the standard deviation of x times the standard deviation of y is to basically normalize the correlation measure, or normalize the covariance between -1 and 1. Because if we only looked at the covariance, the issue is that it would be very hard for us to get a sense of whether there's a high correlation between the two variables or not, because the covariance depends on the measurement units, whereas the correlation, like Pearson's correlation, does not. So that's why in practice, when we want to know the strength of the correlation between two variables, we usually prefer to use Pearson's correlation rather than the simple covariance. And what we saw last time was that the Pearson's correlation is an indication of the strength of the linear relationship between x and y. Okay, but there can exist many different types of relationship between x and y, and it's not always going to be linear. So that's where Spearman's correlation will play a useful role. So let's have a look at Spearman's correlation. So Spearman's correlation coefficient measures the strength of a monotonic relationship between two variables. And what we mean by a monotonic function is just a function that is either always increasing or always decreasing. So if we have a look at the first function, for instance, we can see that it's not linear. There's no straight line that can connect all the points, but it is always increasing. Similarly, for function f2, we can see that it's always decreasing. Whereas the third function is first decreasing and then increasing, which means that it's not monotonic. And for Spearman's correlation, we'll have a measure of whether the relationship between x and y is monotonic. So what's the procedure to calculate Spearman's correlation? Well, you first need to assign a rank to all of the x's. Okay, so you start with your x variable and you rank it. So from low to high. So you assign a rank of 1 to the lowest value, 2 to the next lowest, and so on. Then you do exactly the same thing with y. Okay, so 1 for the lowest value, 2 for the next lowest, and so on. And then you calculate Pearson's correlation coefficient on the ranked values of x and y. So Spearman's correlation will be calculated as follows. So you have R between the rank of x and the rank of y, which is the covariance between the rank of x and the rank of y, divided by the standard deviation of the rank of x times the standard deviation of the rank of y. So for the moment, that might feel a little bit abstract. So let's have a look at an example. So here I have my x variable and I have my y variable. Okay, so the first observation has a value of 23 for x and 35 for y. Second observation is 42 for x and 183 for y. And the third observation is 13 for x and 55 for y. So we can see that the lowest value for x is 13, so that will get a rank of 1. Then the next lowest value is 23, so that gets a rank of 2. And then 42 is the highest value, so it gets a rank of 3. You do exactly the same thing for variable y, so 35 is the lowest value, followed by 55, which gets a rank of 2, and 183 gets a rank of 3. Okay? And then you can just calculate the standard deviation of the rank of x, which is 1 in this case, and for the rank of y, it's also 1. And then you just apply the same formula as we saw last time for Pearson's correlation, but this time on the ranks of x and y. Okay, so the 0.5 5 here is 1 over n minus 1 that you have in the formula for the covariance. So here the sample size is 3. So 1 over 3 minus 1 is 1 over 2, which is equal to 0.5. Okay, and then you take every single observation. So here you start with the first observation. So the first observation is this one. So for x, the first rank is 2, and the mean rank is 2, because 1 plus 3 plus 2 divided by 3 is equal to 2. Okay, so we get 2 minus 2 times, well, 1 minus 2, because there are 2, the mean of the rank of y is equal to 2. And then following the formula for the covariance, you multiply those two terms. Okay, and you do the same thing for the second observation. So for the second observation, for the rank of x, we get 3 minus the sample mean of the rank of x, which is equal to 2, times the rank of y for the second observation, so 3 minus the sample mean of the rank of y, which is 2. And then you do the same thing for the third observation, right? And that will give you the covariance between the ranks of x and the rank of y, divided by the product of the standard deviations of the rank of x and the rank of y, which is 1 times 1 in this case, okay? So the correlation measure that we get, in this case, Spearman's correlation measure, is equal to 0.5. So let's have a look at what that means and how we can interpret Spearman's correlation. So Spearman's correlation coefficient also always falls between -1 and 1. And that makes sense because fundamentally it's just Pearson's correlation, but just on a modified set of variables, okay? And since we know that Pearson's correlation measure is always between -1 and 1, Spearman's correlation also will always fall between -1 and +1. And a correlation of +1 indicates a perfect increasing monotonic relationship between x and y. And a correlation of -1 indicates a perfect decreasing monotonic relationship between x and y. And a correlation of 0 indicates no monotonic relationship between x and y whatsoever. And the closer the coefficient is to either -1 or +1, the stronger the correlation between the variables. So Spearman's correlation can be used with ordered variables or interval variables. And if you remember from the last video, for Pearson's correlation, we could only use it with interval variables. So that's one of the advantages of Spearman's correlation measure, is that we can use it also with ordered variables. So it's a particularly useful measure when the relationship between x and y is not linear. And Spearman's correlation coefficient can also be useful when there are a lot of measurement issues with x and y, if we can assume that the rankings are still accurate, because that could distort Pearson's correlation quite a lot, whereas if the rankings still remain the same, it won't affect Spearman's correlation coefficient as much. So Spearman's correlation coefficient is less affected by outliers than Pearson's correlation coefficient. So let's have a look at those different graphs, and we can see that those two measures can sometimes be quite different depending on the shape of the relationship between x and y. So for example, here, we can see that there's a monotonic relationship between x and y, okay? When x increases, y also always increases, but it's not linear. So Spearman's correlation measure will be 1 because it's perfectly monotonic, but we can see that Pearson's correlation is lower, 0.88, because if we look at a linear fit, it's not perfect, okay? It's still relatively high, but it's not perfect. Now, in a case like this, where the relationship is still positive, but not very clear, then we can see that those two measures are virtually identical. And when you have outliers, we can see that Pearson's correlation can actually be quite low. For example, here, 0.67, which is much lower than you might expect, given that you can see that the relationships seems to be like this, and then you just have a couple of outliers. And Spearman's correlation is less affected by those outliers, and so the correlation measure is still much higher, which shows that with outliers, Spearman's correlation can have an advantage. So that's it for today's video on Spearman's correlation measure, and I look forward to seeing you in the next video.